In today's fast-paced gaming world, optimization isn't just an option, it's essential. Whether you're targeting the web, pushing the limits of XR, or reaching millions on mobile, Unity 6 provides the tools, and in this video we'll demonstrate some optimization tips to get the most out of your game, from profiling and memory management to fine-tuning your graphics. We'll cover key techniques to enhance your game's performance, ensuring a smooth and immersive experience for every player. So let's dive into these essential tips and best practices to optimize your game across multiple platforms. In this tutorial, we'll be looking at an unoptimized VR game and how we can improve performance through a process of profiling and optimization. The game's built in Unity 6, using the universal render pipeline and leveraging the XR Interaction Toolkit for the VR integration. It's a simple game that challenges the user to complete an assault course in the fastest time possible without falling into the pit of spikes or being struck by the swinging mallets. All the artwork is in place, from the trees to the mushrooms, with some simple logic controlling the assault course features. But until now, it's completely unoptimized. When optimizing your project, the first step is to benchmark current performance against the goals of your target devices and understand the main bottlenecks. To begin, press play, and then we'll open the stats window. Now, with the game paused, we can take a look at our stats. This is going to give us a snapshot of how our game's performing. While profiling on the actual target device gives you the most accurate statistics, starting out in the editor and using the stats window here is a good starting point. A common way that gamers measure performance is with frame rate, or frames per second. However, it's recommended that you use frame time in milliseconds instead. Consider this graph of frames per second versus frame time. Frame time, the time it takes to render each frame, directly affects frames per second. For example, moving from 900 frames per second to 450 frames per second is just a difference of 1.1 milliseconds per frame. But it looks like a big drop. On the other hand, the difference between 60 frames per second and 56.25 frames per second is also 1.1 milliseconds. But the change seems less dramatic. That's why developers focus on frame time rather than frames per second to measure performance. Keeping it within target ensures smoother gameplay regardless of how the frames per second number appears. For example, a VR game such as this one, we'd be looking at a time budget of 11.1 milliseconds, and this is calculated by dividing 1000 milliseconds by the required FPS, in this case 90, which would leave 11.1 milliseconds. Alternatively, if you're looking at console, for example, you might be targeting 60 frames per second, which would leave you a time budget per frame of 16.6 milliseconds. And for this VR game, being able to achieve our time budget of 11.1 milliseconds is particularly important, as it's essential to avoid causing nausea or discomfort to the players. By looking at the statistics here, we can see that this VR game has a time per frame of 45 milliseconds, or 22 frames per second. So we're currently 33.9 milliseconds over our time budget, so this will be an area that we can look at in more detail using the profiler in a second. Let's inspect the CPU times. The CPU main of 45 milliseconds, this number represents the amount of time that the main thread of the CPU is taking to process each frame. The main thread handles game logic, physics, input, and other core tasks. A high main thread time can be caused by complex scripts or game logic, heavy physics calculations, expensive update functions, inefficient object management. This is certainly over our time budget per frame. The render thread at 41.4 milliseconds represents the amount of time the render thread takes to prepare the frame for rendering on the GPU. The render thread handles tasks like culling, batching, pairing draw calls, and a high render thread time could be due to a high number of draw calls, complex or expensive shaders, heavy use of real-time lighting and shadows, inefficient batching, or overdraw. When thinking about optimizing our game, we need to establish where the bottleneck is, whether the CPU or the GPU is the limiting factor for achieving higher frame rates. A game is considered CPU bound when the CPU is the primary factor limiting the frame rate. And this happens when the main render thread on the CPU takes longer than the GPU to process each frame. In this example, the main thread time is 45 milliseconds, and the render thread time is 41.4 milliseconds. If these values are higher than the GPU frame time, it indicates that the CPU is doing too much work, or there are inefficiencies in how the game is managing its logic, physics, or rendering tasks. Alternatively, this game could be considered GPU bound if the GPU was the limiting factor, and that will occur when the GPU takes longer to render a frame than the CPU takes to prepare it. This flowchart provides a structured approach to identifying performance bottlenecks. By systematically following each step, developers can determine whether the game is constrained by CPU or GPU limitations, or if there are other underlying issues affecting performance. Let's move to the Unity profiler to further analyze the game's performance. The profiler is a crucial tool for examining where the game is spending its time and helps pinpoint whether the bottleneck is related to CPU or GPU activity. Open the profiler, click on Window, Analysis, and Profiler. Establishing a consistent end-to-end profiling workflow for your game is crucial, and it all starts with a simple 3-point procedure. Profile before making major changes to establish a baseline, profiling during development to track and ensure changes don't break performance or budgets, and profiling after to prove that the changes have had the desired effect. For the sake of this demonstration, we can consider this establishing our baseline. Within the profile modules, we're going to check the GPU usage, and we can also give it a target frame time. I've got mine set to 90 frames per second as I'm targeting a VR device, and then I'm going to go ahead and press play. Now we've got a good segment of data, let's pause it here. Clicking on the Highlights tab will allow us to move up and down the timeline to see a snapshot of our target frame time, which is 11.1 milliseconds, against the actual achieved time by both the CPU and the GPU. We can see here in all instances, frame by frame, always considerably over that time budget. And now we can dive deeper into the profiler to actually ascertain to where the bottleneck is coming from. And in the Highlights window, if you're unsure about what to do next, it does actually break it down for you and give you a little bit of assistance. We're going to go ahead and inspect the CPU usage. You can see here 45.27 milliseconds was allocated to the player loop, so we can drill down into this piece of information a little bit more. This extends to show us that the frame events.xr begin frame is 38.95 milliseconds, and then we have the gfx.wait for render thread 38.92 milliseconds, with the semaphore.wait for signal taking 38.92 milliseconds. The gfx wait for render thread is a performance marker in the profiler that indicates the main thread is waiting for the render thread to complete its tasks. This often happens when the rendering workload is heavy and the CPU must wait for the GPU to finish rendering before it can proceed with the next frame. So if the GPU is overloaded with complex tasks such as heavy post-processing, complex shaders, high polygon models, or lots of objects on screen, it will take longer to finish rendering the current frame. This delay causes the CPU to wait for the render thread. So with this in mind, let's take a look at the GPU usage module. Investigating the GPU section reveals that it's taking 59.62 milliseconds. Exploring this further, we can see that the execute render graph is taking 41.3 milliseconds. Execute render graph in the profiler indicates the time spent on processing all the rendering commands defined in the render graph for a single frame. Render graph is a system used in Unity's scriptable render pipelines to manage and optimize a sequence of rendering commands, or passes, that are executed by the GPU. With the data telling us that the CPU is waiting for the GPU, and for the GPU to be taking more time overall than the CPU, this data indicates that this VR game is currently GPU bound. Let's review the graph to assist our investigation. We'll start at the top. We've looked at the Unity profiler and we are not in the frame time budget, so we'll move down to the no. Is the main thread waiting for another thread? Yes, it's waiting for the render thread. Are we waiting for the GPU? Yes, we are. And then this will tell us where the bottleneck is, and it informs us we are GPU bound. You can then move on to the next steps, which is to look at the GPU debugger, shaders, graphics, and quality settings. And the possible fixes would be to optimize shaders, mesh or texture compression, or resolution, overdraw, and post-processing. To continue our investigation, before we leave the profiler, let's have a look at the rendering module. Moving to the rendering profiler, in this frame we observe a total of 1200 draw calls, indicating the number of individual rendering commands issued from the CPU to the GPU. Using draw calls is essential to enhance performance. We also note 1160 batches, where objects are grouped to minimize draw calls. Of these, dynamic batching has resulted in just one batch draw call. Static batching and instancing, however, show no batch draw calls, suggesting an opportunity for further optimization by combining more static objects or utilizing GPU instancing. In relation to geometry, this frame processes 1.8 million triangles and 1.3 million vertices, which represents the complexity of the scene. Optimizing the number of triangles and vertices can help maintain a balance between visual fidelity and performance, especially in performance-critical scenarios. To improve this, we should focus on optimizing draw calls through batching, reducing geometry complexity, and streamlining texture and shadow usage to ensure smoother gameplay. Before we go ahead and make those optimizations, first need to follow our diagram and ensure we have appropriate quality and renderer settings. Before starting with our mesh optimizations, it's important that we give our Unity project a good strong foundation for optimization. Using the universal render pipeline and the high definition render pipeline, you can assign different render pipeline assets that directly affect how your game or application is rendered. And the goal is to balance visual quality and performance to suit the specific device you're targeting. Let's take a look at the render pipeline asset we're currently using. Go to the project settings, click on quality, and you can see here we're using the PC High Universal Render Pipeline asset. With Unity 6, when you create your project using one of the scriptable render pipelines, you'll get access to a set of presets that will allow you to tailor your renderer to suit your needs. For our game, because it is going to be played on a VR device, we're going to be using our mobile render pipeline asset. So we'll go ahead and drag that in to our rendering section. They continue. I'll change the current active quality level to mobile. We can take a look at this render pipeline asset by clicking on it and then bring it in the inspector. You will see here the different areas in which we can adjust and tailor it to our specific needs, giving you the maximum flexibility over how your game is rendered. By tailoring our rendering, it ensures that our game uses the appropriate rendering features and settings for the targeted device. This will help us leverage the strength of each platform and avoid unnecessary overhead, ultimately delivering a better experience across all devices. So now we've got a good strong foundation on which to build, let's take a look at some of our meshes. Now we're going to take a look at our models to see where we can optimize reducing draw calls, mesh complexity, and enhanced texture usage. And when doing this, there's always a trade-off between the fidelity of our meshes and performance. And this is important no matter what you're deploying to, be it console, PC, web, or XR. Having optimized models is going to help your performance. Let's start by taking a look at the trees. You can see that it's made up of several different components. It's got different meshes for different parts of the tree. They've all got their own material assigned to them as well. And in terms of mesh complexity, if we switch it to a wireframe, you can see that it's quite a dense mesh. There's definite areas where we can reduce the topology and get a more performant model. Then looking at another model in the scene, let's have a look at one of these mushrooms. It looks very high poly. If we turn on our shaded wireframe, we can see that it is indeed quite dense. There's a lot of detail in there that can be reduced. See, the fence posts also have an incredible amount of detail. We can look to reduce detail there. There's not very many meshes in the game. We can very quickly go through our models and optimize them. And that's something you would look to do in your 3D package. Here's my tree next to the other tree in Unity. You can see the one on the left is the one we had before, and the one on the right, the gray one, is the new one that's been optimized. So now we would go through that entire process with the different meshes that we have in our scene, optimizing them all to make them more performant. There we are. So I've gone through all of those assets. I've replaced each one with their new low poly counterparts, which should now be a lot more optimized, reducing the tries and the verts in the scene, and also drastically reducing the draw calls as well. Let's go ahead and press play, and we'll look at our profiler under the rendering section to see what performance improvements we've made. I've paused the game here whilst we're running, and you can already see noticeable improvement in our frame time. It's still higher than our target, but compared to where we were at the beginning, we're starting to get noticeably closer to our 11.1 milliseconds. Under the rendering, we can see we've dramatically reduced our draw calls. We're now down to 286, and our triangles and verts are no longer in the millions. With all the trees and the mushrooms and the rocks and everything else in the scene, we're now down to 128,000. Let's continue our optimization here and have a look at applying our materials and introducing static batching. Let's take a look at optimizing our textures and materials. If we take our tree as an example again, previously each tree comprised of 6 different meshes with 6 different materials. But when optimizing our tree mesh, we can see that it's one mesh with one material. And this material is actually shared across multiple meshes, as we've taken our textures and combined them into one single texture sheet. Reducing the number of textures by combining them like that can reduce draw calls. Let's go ahead and apply our textures by dragging them in to the relevant slots. Here you can see that not only do we have the green tree, we also have the brown trees as well, using the same material, the grass clumps, and the rocks. Let's take a closer look at our textures. This texture is currently 9.5 megabytes, a resolution of 4096 by 4096. I'm going to go ahead and reduce the size of this texture by half. Let's see what this reduces down to. This reduces it down to 2.4 megabytes with no noticeable loss of fidelity within our scene view. We can try and go even lower to 1024, hit apply, and now we're down to 0.6 megs. Additionally, we can go ahead and mark use crunch compression and apply. Crunch compression is a lossy method that significantly reduces texture file sizes while preserving visual quality. It is especially useful for platforms like mobile and Unity web builds where minimizing download times and memory usage is crucial. While it may slightly increase load times, crunch compression is a valuable tool for optimizing asset size in performance-sensitive environments. This is again going to come down to a balance between performance and visual fidelity, and it's up to you to make a judgment call on how far you're willing to compress your textures before it sacrifices the quality of your game. Compressing your textures is particularly important for all devices, but particularly for deployments that are going to be used as Unity web builds, where file size becomes hugely important to minimize big downloads for the user. While crunch compression effectively reduces texture sizes, it's essential to regularly monitor memory usage to ensure optimal performance. The memory profiler allows developers to capture a snapshot of memory allocation, making it easy to identify large textures and other assets that may be consuming excessive memory. By using this tool, you can detect memory bottlenecks early and ensure your compressed assets are effectively managed within the game environment. A full tutorial on using the memory profile is available, and the link can be found in the description. Now we've gone through and found all our large textures in the game and adjusted their resolutions, you can see that I've actually dropped them even more than 1024, particularly the ambient occlusion maps, the metallic smoothness, and the normal, to the point where I was starting to lose visual quality on some certain objects up close. And the last piece of work we're going to do on our textures is to look at the build settings. Selecting the Android platform, it will set the texture compression to ASTC. Doing this because ASTC provides high quality texture compression while reducing memory usage and improving GPU performance. By using ASTC, we ensure that our textures look great while minimizing the impact on frame rates, which is especially crucial for mobile and VR platforms. This helps us achieve a smoother and more efficient gameplay experience. But now this is done, let's go ahead and look at the last piece of optimization on this scene before we check it in the profile again, and we'll go ahead and take a look at batching. Draw call batching is an optimization technique that combines meshes so that Unity can render them in fewer draw calls. Static batching combines multiple static objects into a single draw call, reducing the calls sent to the GPU, improving rendering performance, particularly in scenes such as this with many static objects. In order for static batching to work, we must mark any meshes that don't move as static in the inspector. Then in the project settings, if we go to player, we need to make sure that static batching is checked. And another technique would be to have a look at the GPU resident drawer, which is available in the render pipeline asset. And the GPU resident drawer, which is a new feature in Unity 6, is a GPU-driven rendering system designed to optimize CPU time, offering significant improvement benefits, especially for those projects using the URP and the HDRP. It supports cross-platform rendering, including high-end mobile platforms using Vulkan and Metal. It's designed to work out of the box with existing projects. So to enable this, change from disabled to instance drawing, and you'll get a warning saying the batch render group variant setting must be set to keep all. You need to go back to our graphics settings, and then where we have the batch render group variant, select keep all. Going back to the render pipeline asset, you'll notice that when we selected instance drawing, that we're also informed that static batching is not recommended when using the GPU draw submission modes. And this is because it introduces unnecessary memory overhead and reduces runtime flexibility. These techniques are already optimized for reducing draw calls and keeping data on the GPU, so static batching can actually create performance inefficiencies by competing with these processes. For dynamic, large-scale environments, it's best to rely on the GPU resident methods alone for optimal rendering performance. In the next section of this video, we're going to take a look at optimizing our lighting. When developing for XR mobile or web platforms, optimizing lighting is crucial to maintain performance, as dynamic lights, particularly in forward rendering, can significantly degrade frame rates and increase the power consumption, which is particularly problematic on resource-limited devices like consoles, mobile phones, and VR headsets. Instead, consider using alternatives such as custom shader effects or light probes for dynamic objects, which would simulate lighting conditions with minimal performance impact, and for static objects, baked lighting provides high-quality illumination without the overhead during runtime. With that in mind, I'm going to set my light mode to baked, and then open my lighting tab. If we don't have this here, you can get it by going Window, Rendering, Lighting. And I'm no longer going to be using real-time global illumination, so I can turn that off. I am going to be baking my global illumination, so make sure that's checked. Next, we'll go ahead and take a look at our lighting mode. We have baked, indirect, subtractive, or shadow mask. For our lighting mode for VR, I'm going to choose baked direct, which is great for static scenes to maintain high frame rates, and that'll be for the same for web. Mixed scenes, you might want to consider using the shadow mask to balance dynamic shadows with baked lighting. And for console, for scenes with both static and dynamic elements, shadow mask offers the best balance between visual quality and performance. And subtractive mode can be considered for simple scenes with single dominant light source to further optimize performance. Moving down, for our light mapper settings, I'm going to change it to the progressive GPU light mapper. which is production ready in Unity 6, designed to dramatically accelerate lighting data generation by leveraging the power of the GPU. The remainder of the settings will control the bake quality, and the higher the quality, the longer the bake time. For testing, I will set some settings for a faster bake. The important settings here in terms of runtime performance and memory will be max light map size with a value of 1024. This gives us a balance between texture memory usage and light map quality. The light map compression, high quality is suitable for retaining more detail in light maps, but if speed or memory usage is a concern, we could lower this to low quality. The speed, I'm going to put mine down to low quality, just to see how my initial bake looks, and we can always adjust these after. With these settings, we can go ahead and generate our light maps. So here we have our bake. It took 2 minutes and 42 seconds. This generated 18 bake light maps. There's certain things that can be done to help reduce that number. For example, you could select a mesh in your scene and adjust its scale in the light map 0.25, a number between 0 and 1. You can go around doing that for different objects in your scene. The things that are going to be nearer the player, you want nearer the 1 because it gets more resolution in the light map. Things that might be far away that don't need as much detail and have a smaller scale, such as the mountains in the background, currently set at 0.2. And for these trees that are close to the player in this central area, we could actually go and turn off cast shadows on all the nearby trees. And what we can do is create a plane that sits underneath this tree with a texture on it that looks like the shadow of the tree. For example, I have this shadow prefab that I've made. If I drop this in the scene, zoom in on it, you can see that it looks like the shadow of a tree on the ground, but it's actually just a quad and with material on it, simple lit, which is just a picture of a tree. It's made to look like a shadow. I can then drag this under my tree, position it correctly and scale it according to the tree that I want to give it the shadow to. And then on this particular tree on its mesh, because the cast shadows are off, there'll be no shadow on the ground other than our fake one, which looks nice and crisp. So we can create fake shadows for the objects that are close to the camera, making them look high resolution. But everything else further away will be using the default light maps. And here is the result of that bake and the impact that those fake shadows have had on the ground, where you see in the distance those trees are all using a light map shadow on the ground. And you can always play with the colors on whatever material you've got to make that blend feel more natural. And additionally, we have a light probe group in the scene that is lighting the dynamic objects. New in Unity 6 is the adaptive probe volumes, which we can now upgrade our current light probes to this new system. Unity 6 introduces adaptive probe volumes, a solution for global illumination that enhances both performance and visual quality across various platforms, providing dynamic and efficient lighting in complex scenes, particularly for mobile and lower-end devices, while leveraging advanced capabilities on high-end platforms. This system supports real-time lighting transitions such as day and night cycles, and developers can gain fine control over light probe density. Currently we're using light probes in our scene, but let's upgrade them to the new adaptive probe volumes. To get started with adaptive probe volumes, click on the lighting tab, and you'll notice at the top we have the adaptive probe volumes button. Go ahead and click. We'll have a warning that says the current URP asset does not support adaptive probe volumes, so we'll go ahead and open our current URP asset. And then a window will pop up where we can navigate to our lighting section. And then under the light probe system, change from light probe groups to adaptive probe volumes. To create an adaptive probe volume, right click in the hierarchy, go down to light and select adaptive probe volume. This places an adaptive probe volume in the scene, which we can then move around our scene and place in the areas where we'd like our adaptive probe volumes to be. This particular game would suit 2 adaptive light probe volumes very well. We could have one that encompassed the main area that the player is going to be in, and this could be a more detailed adaptive probe volume, where the max probe spacing is a lot smaller. Then we could use another one that encompassed the whole scene with a very high max probe spacing. So I can position this probe volume in my player area, and to help visualize the adaptive probe volume, we can use the render debugger, which is available in Window, Analysis, Rendering Debugger. Select probe volumes, and checking display cells and display blocks, and also display probes. Let's go back to our adaptive probe volume. Now we're ready to bake our adaptive probe volume. We can go ahead and tick Bake Probe Volumes. Once it's baked, we'll then see the probes within the volume, and we can see that the URP has used bricks with different sizes to match the amount of geometry in different areas of the scene. Small bricks, indicated by the purple section, represents probe distance of 1 meter, and then the blue represents probe distance of 3 meters. So we have an adaptive probe volume in the area where the player is going to spend most of the time, which is around the assault course. But we can create another adaptive probe volume, which we can use to encompass the environment. So we could use the adaptive probe volume size for fit to all scenes, fit to scene, or fit to selection. I'm going to click fit to scene. You can see that that volume has encompassed my entire level. I want to override the probe spacing for this particular volume. Because it is the environment, it doesn't need to be as detailed. So I can go ahead and check that box and then drag all the way to 27 meters. I can then go ahead and bake this probe volume. Here we notice that the scene has been separated into bricks of 27 meters represented by the blue and the pink at 81 meters. Now my scene is a very simple lighting setup. The lighting doesn't change. So I've only touched on the very basics of the adaptive probe volumes. But if you'd like more information, then check out the link in the description. After reducing object scale and light map, using adaptive light probes to light the majority of the scenery, and leveraging fake shadow planes, we've reduced the number of light maps to one single 2048 by 2048 light map. This is highly beneficial for VR, mobile, and web platforms. It reduces memory usage, improves performance by minimizing texture swaps, and results in a smaller build size, which is crucial for faster download times in web builds and more efficient use of storage in mobile and XR. We've now performed the primary optimization tasks to reduce our GPU bottleneck. We've focused on reducing draw calls, we've optimized our meshes, reduced the number of materials by combining textures, and improved our lighting workflow. And now it's time to use the profile analyzer to take a look at how our game is performing now we've made all those optimizations and compare it against where we were before we started the optimization process. To access the profile analyzer, we'll go to Window, Analysis, and Profile Analyzer. You then have some instructions here if you've not used it before. It informs us that to gather data, we must open the Unity profiler, capture some profiling data, then we can use the Pull Data button to grab the information from the profiler and start our analysis. So to get started, I'm going to go ahead and enter play mode and start getting data into the profiler. I'll pause the game there and I've got a good segment of data. I can then use the profile analyzer to pull the data and I can stop running my game in the background. Let's have a look at how our game is now performing. Well, the profile analyzer is a very powerful tool. You can see here there's lots of data within this window. Within this pull data section, we have the frames that were captured, where we can left click and drag and select a selection. And then top right, we have the frame summary that tells us within our selection we have 235 frames. Our max frame time within that selection was 16.34, and our average frame time was 9.06 milliseconds. So in terms of our frame time budget of 11.1 milliseconds for 90 frames per second in VR, we're now starting to get below that figure. The top 10 markers on medium frame lists the top 10 most expensive markers contributing to frame time, and the player loop, as seen here, has a mean time of 5.75 milliseconds. So this will be the main contributor to our frame time currently. And then we have the marker details for currently selected range. This is our currently selected range. And then you have each marker along with its associated time in ascending order. Well, what's great about this data is, although it now tells us that we've made a great improvement, we can now see by how much, because what we're able to do is compare two sets of data. So at the beginning, before I started optimization, and I saved some data, so I can now load in that data by going to compare and loading in the data that I stored earlier before our optimizations. So we have our data across the top. We have a frame range of 300 frames of both sets of data from the optimized version on the top and the unoptimized version on the bottom. And within our frame summary, you can instantly see that we have a huge performance gain between our optimized and unoptimized versions. If we look at the mean frame time, which is the average frame time, for our optimized version, we're now hitting 9.44 milliseconds per frame compared to the 53.43 milliseconds on the unoptimized version. So we've improved it by 43 milliseconds. Let's have a look at the top 10 markers on median frames. Massive improvement in player loop, a 32.85 millisecond reduction in the player loop alone, leading to drastically improved frame times. Rendering and GPU synchronization, there's a major reduction in time spent waiting for the GPU. Markers like GFX wait for render thread and semaphore wait for signal, which suggests that the rendering pipeline is much more efficient. In terms of XR performance, markers like XR begin frame and XR update show huge improvements, likely making the VR experience much smoother and reducing latency between frame times. So we've taken a look at our GPU optimizations and we've made a huge impact. We are getting the frame times that we're looking for, with a mean frame time of 9.44 milliseconds, with 11.1 milliseconds being our target, but there are still optimizations we can make. We can now turn our attention to the CPU optimizations. For example, the left median shows update script run behavior update. It's currently at 1.79 milliseconds, and this can be an area for us to optimize further. If we move back to the profiler, if we scroll through our timeline here, you can see that we now have the update script run behavior update marker. If we extend this down, we can see we have behavior update, extend that down again, and a couple of scripts are showing up in the profiler as taking a significant proportion of our time budget at 1.25 milliseconds and 0.5 milliseconds in both the pendulum swing update and the timer script update. We've got log string to console indicating that we've probably got some debug.logs going on in these scripts, and we should take a look at these scripts for further investigation. So the CPU optimizations will become our next focus. Two of our scripts have shown up in the profiler. One is the timer, and the other is attached to each of the pendulums that are swinging left and right. Now, even though in the profiler, the timer was only 0.5 milliseconds and the pendulum swinging was just over 1 millisecond, with an 11.1 millisecond frame budget, these times can be quite significant, and altering our scripts will improve our frame time. Let's have a look at the pendulum swing script. Here we can see that we're using the start method and the update method. The update method is called once per frame, meaning that any debug log statements within it will be potentially executed every single frame. This can cause significant performance issues, especially in high frame rate environments like VR, mobile, or web, where the overhead of logging can lead to lower frame rates. Debug.log creates strings internally, which can lead to memory allocations. These allocations contribute to increased garbage collection, causing spikes in performance due to memory cleanup processes. And this can be particularly problematic on platforms with limited resources. These aren't necessary anymore in this application, so we're now going to remove them. Additionally, in this script, the pendulum arm that we're swinging is a child object. As we can see by clicking on the swing arm model, where we have our pendulum swing script, and we have the swing arm as a child. Currently, in our script, every frame we're using transform.getChild and then setting its rotation. In this instance, it would be better to cache the transform that we're rotating, and we can do this by creating a variable called swing arm, which is a transform. We can then assign this transform in the inspector, or we can assign it in the start method by assigning swing arm to the first child object. Then we can simply, in the update function where we're currently getting the child every frame, we can then simply say swing arm.transform.rotation. So removing transform.getChild out of the update loop, we're removing that search operation every frame, which is then going to remove that unnecessary processing, especially if the object hierarchy is deep or the game runs at high frame rates. Let's now take a look at our second script, which was the timer script. You can see here we have the start and the update method. And in the update method of our timer script, we can see that we have an update timer display, which is updating the text on the display to see how long the player has been playing. If we click on there, we can now see that every frame this update timer display is running. And we have very much the same issue as the pendulum swing script in that we're writing to the console to debug the current time that the game has been running. And then every frame we're also getting the text component of the object that this script is sitting on and adjusting its value. We no longer now need to use the debug.log statement. Everything is working just fine. So we can go ahead and remove that. And as before, we can go ahead and cache a reference to the text object. So we have our public text mesh pro UGUI timer text. And we just need to make sure that's assigned either in the inspector or we can assign it in our start method. Once we've cached our text object, we can then go ahead and amend our update timer display. We're no longer going to be getting the component every single frame. We can now use our cache value, which is timer text, and then just amend its text value. Now, if we run the game, let's check that our optimizations on our scripts have had an effect, and then go to the profiler. We can see that now under our update.script run behavior, we've now reduced our pendulum swing down to 0.02 milliseconds, where before it was above 1 millisecond, and the timer script 0.5 milliseconds, it's now 0.03 milliseconds. Let's consider some other optimizations that we can make and discuss occlusion culling and see if it's appropriate for this project. Our next optimization technique is going to be to use occlusion culling to remove hidden objects. Objects hidden behind other objects can potentially still incur a render cost. While frustum culling outside the camera view is automatic, occlusion culling is a baked process. We need to make sure our objects are marked as static occludees or occluders, and then we can use window, rendering, occlusion culling. And then we can go ahead and hit bake. Then once the bake is performed, we have our occlusion data that we can then visualize in the scene. Whilst occlusion culling can be a powerful tool for reducing the load on rendering, its effectiveness depends on the complexity of the scene. For example, in situations with low overdraw, like this scene, the additional overhead of occlusion culling could outweigh the performance gains. So it's important to profile before and after applying certain features like occlusion culling to ensure that it truly benefits performance. A new feature for Unity 6 is GPU occlusion culling. It significantly improves rendering performance, especially in scenes with complex geometries and many occluded objects. It boosts the performance of game objects by reducing the amount of overdraw for each frame. To activate, locate the render pipeline asset that you're using. Then under the GPU resident draw section, we have the GPU occlusion culling. We can go ahead and mark that box. When optimizing a game, it's important to look at all aspects of performance, including physics, even if they don't appear to be causing issues right away. While in this example, the physics system isn't currently affecting performance, it's always good practice to optimize wherever possible. By reducing unnecessary physics calculations, we can ensure the game runs smoothly across different platforms, especially on mobile, web, and XR. With that in mind, the first step we'll take is to ensure that pre-baked collision meshes is checked within the project settings. In the project settings, under Player, locate Optimization and check pre-baked collision meshes. Pre-baking refers to the process of creating these collision meshes ahead of time rather than generating them dynamically at runtime. By pre-baking collision meshes, you effectively reduce the number of calculations the physics engine needs to perform. This is critical for maintaining performance, especially on resource-constrained platforms like mobile devices or in web-based games. Our next step in optimizing the physics is to navigate to our Physics, and then Settings, and then under the Shared tab, we can now see our physics matrix. Each row and column represents a layer in your game, and you can enable or disable collisions between layers by clicking or unchecking the corresponding cells. Optimizing this matrix is crucial because it reduces the number of collision checks the physics engine needs to perform. In Unity 6, this process is even more efficient, with better multi-threading in the physics engine, leading to faster calculations and improved performance. The updated layer collision matrix interface also allows for easier customization and visualization of layer interactions. I can now go ahead and uncheck the layers that don't need to collide with each other. In this specific project, Player is on the player layer, which I've specifically configured to only collide with the necessary layers. By carefully managing these interactions, we reduce physics overhead, leading to more stable frame rates, especially on resource-constrained platforms like mobile, web, and XR. Now that we've optimized the layer collision matrix and reduced unnecessary collision checks, we can further improve the physics performance by looking at colliders we're using on our game objects. The type of collider you choose can have a significant impact on performance, especially when applied to complex mesh objects. Simple colliders like box or sphere colliders are far more efficient than mesh colliders, which calculate collisions based on the exact shape of the object. Let's take a closer look at the colliders in our scene and explore how we can optimize their usage for better performance. Let's have a look at a fence post. You can see here we have our fence post mesh, and we also are using a mesh collider. This mesh collider calculates collisions based on the exact shape of the object. We can improve this object in a number of ways. First of all, we can use a box collider instead of a mesh collider, and we can also separate the art from the collider to allow greater flexibility in terms of both art and development. What does that exactly mean? If we look at this fence post, we can see we have a game object. It's called vertical fence post. And inside this object, we have the artwork for it, which is simply just the mesh and the material. And then separately to that, we also have a collider, which is just a box collider that wraps around the form of the object. These two are separated because if our artwork was to change, we wouldn't have to worry about adjusting the collider. When this object was updated, we would simply replace the artwork inside the prefab, and the collider is its own object. And then if there was any scripts or interactions, you could put this on the parent object and link up any variables and not have to worry about losing them if the artwork was updated and you had scripts on the artwork. We could then turn this fence post into a prefab by dropping it into our prefabs folder, and now you can populate this around and replace the existing ones, making it much easier to update and maintain. By updating our colliders from complex mesh colliders to simpler primitives like boxes and spheres, we've significantly reduced the computational load of our physics system. These primitive colliders are much more efficient to process, especially in large or dynamic scenes. While some objects may require precise collision detection, most can use these optimized colliders without sacrificing gameplay accuracy. This approach not only improves performance, but it also helps maintain smoother frame rates, especially on mobile and XR platforms. This concludes the optimizations for this particular project. Let's take one last look at the profile analyzer to see how we finished up. We'll take our current data from the optimized version and also our unoptimized data on the bottom and compare a range of 203 frames. We can see that our frame time on average was 8.89 milliseconds. compared to 50.66 for our unoptimized version, with a difference of 41.78 milliseconds. Meaning that everything we've done for all of our optimizations, from the GPU optimizations through to the CPU optimizations, has had an impact and has managed to get us below our target frame rate of 11.1 milliseconds. In this video, we only had time to show you a few techniques specific to this demo project, but there is of course so much more you can do depending on the nature of your project. To learn more, our 2 performance optimization ebooks offer hundreds of actionable steps, and you can find a link for those in the description. Optimizing performance is crucial, especially for platforms like VR, mobile and web, where every millisecond counts. By applying the techniques we've covered in this video and reading our optimization ebooks, you can significantly reduce memory usage, improve frame rates, and enhance the overall user experience. And finally, thanks for watching. I really hope this helps you take your project to the next level.